Okay, so a couple of announcements today before we move back into continuing differential equation fluid motion. So there are two questions over in the factor to go from the from our definition of the stress tensor for the Newtonian fluid. So there were a couple of questions. I went to your textbook and the notes, and you can derive where that goes from just giving your textbook, including the definition of Newtonian of the derivative of the Newtonian stress tensor. Sorry, this is factor 2, but don't worry, factor 2 goes away because of continuity. So I can follow through this derivation that I wrote out and uploaded on the files. So we don't have to, but the curious that factor 2 goes away because of continuity. By applying continuity for an incompressible fluid, we'll get rid of that factor. The other big announcement here is no homework today because we had the exam a week from today. So I didn't like the homework that's due on the day of the exam. Now that does mean midterm 1 is next Wednesday, September 28th. So it's coming up real quick. Same time as class. In this classroom. So expect the room to be quite a bit more full next Wednesday. Let them sit 1 feet apart right before the exam. Open book, open notes, open homework. So I recognize that some of you are going to yeah. So you run out of the room real quick. I was worried about what's going on.
No, I just wanted to see.
Oh, open book, open notes, open homework. I recognize some of you have the book as PDF. You might have my notes and PDFs. So you are allowed to use a computer or tablet to look at these things, but no internet, no chat, no email, right? No discussion with anyone else. So we're really find your answers. So we'll be wandering around the group, sitting in the back. Another thing about the midterm, and this is I give some tips for the class on the syllabus, but one of them that's can be a little bit helpful. Even though it's open notes, one thing that's that students have discussed with me in the past is that they get to the exam, they know something is in their notes, they're going to flipping through dozens of pages, PDFs or whatever to find it, and wasting time that way. So open notes includes if you want to make yourself a 2-page cheat sheet of notes, right, that you have as a physical copy, that's great. Right. I'm not requiring you to do that. I'm not saying that that's the only notes you can have here. But if that's worked for you in the past, then I definitely encourage you to do it. It's very good study. Right? That's kind of the secret of when professors tell you that it's you just get both sides, front and back of a sheet of paper, and take all that, get down and squeeze it as much as I possibly can. And, my cheat sheet will have everything on it. It's like great. That's great. I'm happy to do that. So if that worked for you in the past, though, I strongly recommend you do that here. Just you've gotten everything, and that's again, it's great. It doesn't have you don't have to squeeze on the 2 sides of the sheet of paper, right? But whatever it is, exams will be handwritten on paper that I hand out here. Right, so I'll be handing out the grade scope templates printed out, attached to the back of the exam. And then collecting those, and I'll take care of scanning and uploading. Any questions on that? Yeah.
We need the book for it.
Yeah. So the question is, should you need the book for confidence and guys? I will try to give you most of the information you need as like supplementary information on the exam itself, so you don't have to flip through. I can't promise I'm going to get it. So something like confidence, you should probably have, right? So so by which I mean like the tables in the back of your book, right? So you have there are tables in the back of the book on like common fluid properties and that kind of thing. Should have. I will try to remember to give you all of those in the, but I do expect you know and look up the.
Make this like what we do with the state of the art, so we don't want to come down to the art. Say that.
Yeah, so the question is, okay, you make assumptions, can you say what they are? Yes, definitely can. Now the question is, with, like if, say temperature of 180 degrees and you do this 1,000 kilograms per meter or something, I guess it depends on what the problem's about, right? So if I'm asking you, if I say that we have water at 80 degrees, I'm probably asking you to look up for you to get the water 80 degrees, so you lose points on that part of the problem. You wouldn't lose points on other parts of the problem based on that assumption, right? But at any points that we're assigned to like that thing, you assume your way around. Right? Yeah, in general, yeah, definitely take your assumption, and I'm generous with part of the credit. I want to see the way to work with the problem. Yeah. Sorry. Property table? Yeah, property table was fine. Yeah. Is that what they're on? Or yeah, that's fine. If you're using something that's not from, like if you're going to look at properties in there, might just briefly write that you got the properties in there, so I know if you get you have something slightly different. They're using different. Okay, other question. Yeah. Yeah, you can definitely rip the template off the back of this. Yeah, I can write that out. I mean, if you want to have a separate sheet, that's fine. Make sure your name's on the top of every sheet, though. Because otherwise, with 65 or so, it's answered. Okay, other questions? Yeah.
That's similar to that, if we need more paper and that paper.
Yeah, good question. If you need more paper, so I'll bring in some paper with me. And also other copies of exams that you can write on. And use more than the space it's allowed to. I know some people have a hard time putting things in on the template, or you mess something up, right? And it's easier just to cross it out and keep going than if you try to erase it. So if you need more space, you can definitely use that space. But tell me where it is, right? So give me a set, tell me it's on the extra, on, seat scrap paper or something. Try to make it clear as possible where that is. Again, I'm looking for partial credit. I'm looking for how you solve the problems, right? For most points are. And I want to give you every chance possible to show me that you know how to solve the problems. So tell me where it was. Yeah.
You said this already, but can you use a digital textbook or your digital notes?
Yes, you can use digital textbook, digital notes. Okay, right. Yeah. No internet, but digital textbooks. Yeah.
There's the.
What's that?
No, my bad is wrong.
I do not know where it is. Maybe in the. Yeah, definitely in the bathrooms. Yeah.
In a textbook, right?
Any other questions? Any other questions about, I guess anything, but, especially about the exam of this class. Oh, yeah. Yeah, so about how many problems we have on the exam. So I have not written the exam yet. My answer though is, the pretty close amount of one. It's about what I'm looking for. Now, I'll release exams. Let's bring this one. I'll release exams today. And as I do this, you'll see that the course has changed a little bit over time. So for example, in 2019, we covered points and forces on submerged objects. We did not cover this here in that. We covered definition of pressure, we covered how to use manometers, define pressure, and what the pressure distribution is in the fluid, but not what force on the dam. And there's a question in there on the 2019 exam about the buoyancy force. Right? So if we can get that, we kind of covered it. And okay. I think that's the only one before we release the exam today. I'm going to go through one more time and make sure there's nothing else we have covered. That's one thing. The other thing is timing of the exams. You'll see the exam 2019 and 2021. 2019, that means the exam is too long. It's called one problem, four problems. And it's gonna either been 3 problems or 8 problems. So don't panic if you see that. So I will read some exams. You've seen most of the questions on your homework. Okay. So we start with problem 1 is true false. I think we have about 5 true false statements. It's problem 1. And then problems 2 and 3 on the midterm 2021. The problem 6 and 7 from your homework Tuesday. So you get a sense of time. But you have seen most. I think there's one problem that you haven't seen at all on. Now the points. Yeah, now we have seen, but there's one larger problem that's pumping fluid into a but just
for the thing that whatever.
sorry,
Sorry. On the homework.
Yeah, so the question is it going to be building its way through? Yes, generally that's how my problems tend to be. Right, I have one setup, and I'm asking you a couple of different things to walk your way through it. I guess 2 notes about that. One is you might look at the problem, you look at the biodiesel problem, which is on your homework, and maybe you don't know where to start. I'm trying to tell you where to start with what I'm asking you part A. So that's probably a good place to start. And I try to build the complexity as you go through the problem. Well, let's say you're totally lost on part A, but you know how to start part B, right? And it relies on your answer from part A. Just tell me this is the answer that I compute from part A, right? Give it a variable name, and then proceed through part B. Right, so you may not get it from that for numerical answer, you may not get it. But most of the points are going to be for showing me how to solve the problem. So you still get most of the credit for part B, even if you didn't have that answer for part B. Makes sense? In fact, in the past, actually, if I see a completely correct symbolic answer for, if I'm looking for a numeric answer for part B, you have everything from part A, you don't need the numeric answer on part B. Then I would then you would not get full credit for part B. But if you skip part A, and then found a symbolic answer for part B based on the symbol that you assume, the variable you assume for part A, then I do get full credit for that. Right, even if I was looking for the credit. So try to decouple like A from B as much as I can, just in case it falters somewhere.
Yeah. Does that include like a wrong answer from part A, calculations of correct on part A?
Yeah, I do. Yeah, so calculation part A and your part B answer is only dependent on the calculation. Now, if you've done everything for part B, except for that. Yeah. Yeah.
Homework would be a good reference.
The homework going to be a good reference. I mean, the homework problems that are exam questions are good references for how the exam questions are structured. And the homework is I wouldn't say it's an exhaustive list of everything that could be on the exam, right? Because there's a lot of so for example, the true false questions, I have a lot of concepts, right? I'm basically using true false to test concepts. We've covered a lot of concepts in class. I want to make sure you know those concepts, but I don't really have a good way of assigning homework on those, right? So a lot of the things might get false, are probably not directly in the homework class. Class is the standard for what I expect you to know. So we'll cover in class. It's the standard for what I expect. And the homework, I'm trying to practice on concept we cover in class. But I'm also trying not to make the homework really hard. Other questions?
I have a question on like number 7 homework.
Let me ask you now, or,
Maybe after class, talk about specific questions about things on the homework. Okay, anything else? Okay, just as a reminder, I've been using Ed. If I get a question on the homework, then I try to make sure it's all Ed. Have you all seen, for example, there was a question on the homework this week? What W Christian was, no problem. There we go, that's some knowledge. So you can check out Ed, if you're having a question. All right. Okay, and you'll see those examples. All right, so so last time we were talking about, we were working on differential equations of fluid motion. We developed the equation of mass balance, right, for that holds for fluid with a continuous variation of velocity. We said that the special case of incompressible mass balance, we have del dot B equals 0 for an incompressible fluid. And then we developed momentum balance, a fairly general form of momentum balance based on stress tensor tau ij. And then we looked at the definition of that stress tensor for a Newtonian fluid and developed an Navier-Stokes equation. Here we have the x momentum piece of the Navier-Stokes equations, the continuity piece of the Navier-Stokes equations, 4 equations total, x, y, z momentum, and continuity. So that was Navier-Stokes. For most of the work that we're going to be doing in this class, those are the 4 equations. Okay, so when we're, for example, we're considering flow through a pipe, we're generally going to be using just those 4 equations to solve for velocity profile, for example. When we're looking at that's in chapter 6. Chapter 7, we'll look at the what are called external flows. We're looking at flow over the outside of some kind of shape, like around a cylinder. We'll talk a lot about flow around cylinders. We'll talk about flow around objects, and a little bit about flow around physical beings or other blades. And there again, we're typically going to just be looking at results from the Navier-Stokes equations, just those 4 equations. But then when we deal with compressible flow, now temperature can vary dramatically, and by ideal gas law, we know that there's a relationship between pressure, temperature, and density. And so when we're dealing with compressible fluids in general, we also need to keep track of energy, right? So today we're going to be developing a differential form of the energy balance. This is mainly going to be applicable to compressible fluids. So to do this, we're going to start as we did for the mass differential mass balance. We're going to start with control volume form. Our heat minus work is the rate of change to the control volume of the internal energy of the fluid, plus the amount that flows across the control surfaces. Sorry, not internal energy of the fluid. Internal energy running into you. This is the internal energy plus kinetic energy plus gravitational potential energy. Right? The energy per unit mass. So that's our control volume form. And one thing to note is that we're going to assume there's no shaft work. We're going to take this control volume and shrink it down to basically smallest size possible. Right, we're going to shrink this thing down all the way to 0 to get it to derive a differential form. And so when we do this, there's no possible kind of turbine shaft or something that could fit inside of a control volume. This is the smallest reported type of propeller blade that I can find. And these things are about 100 nanometers or so across. We're considering no small control volume, there's no shaft work inside of that. And we can simplify our resulting expression using continuity. And this will be the result. So we end up with again heat minus viscous work, right? Shaft work dropped out is rho times the total derivative, right? This P or the uppercase T represents total derivative of the energy of the fluid with respect to time. Plus E dot grad heat plus E grad delta or P delta. And this is within a volume of the fluid, right? So multiplying by the volume. So now the question is, what are these terms, right? So we're going to write out these terms Q and W dot B. And for the heat flux within the fluid, we're going to use Void's law, H minus K grad T. So we choose a vector, right? Vector heat flux. And so now we're going to say that the net heat into the elements is the divergence of the heat flux. So Q would be minus del dot Q. We have here del dot K grad. We're going to plug this into our expression for the Q. We're going, I know I understand we are running a little fast here. We've done a few of these derivations. We're also mostly going to rely on mass and momentum balance in this class. So I just want you to see where this comes from. But not expecting you to have to do this reproduce this whole there. But slow me down. So viscous work. So another way that we can get energy to fluid is by viscous work. It's basically friction between adjacent parcels of fluid, right? So as we have one parcel of fluid, let's say moving in one direction, crossing over another parcel of fluid moving in the other direction, there's friction between those two. That friction is driven by viscosity, and it turns the motion of the fluid into heat. Just like friction on a solid surface between two solids can heat up the interface between the two, turns in this case the work that I'm putting in to sliding this thing across the table is turning that work into heat. The same thing happens within a fluid, and so this viscous work is turning motion of the fluid into friction. Sorry, into heat. And the viscous work is due to stress on each elements of the or even parcel of the fluid. So imagine each surface of this fluid element multiplied by the area to get the viscous force, and then the work is force times velocity. So the work I'm doing here is force times velocity. Same thing for the viscous work term. So what this looks like, you write it out. You get the viscous work minus del dot v dot tau I j dx dy dt. Again, we have this viscous stress tension thing here. And this viscous stress tension is going to depend on viscosity, for example, for Newtonian fluid, and bring it out in for Newtonian fluid, for example, last class. But we can we typically don't use this form. We can simplify and combine with momentum balance to obtain this form of the energy balance. And this is the general form of the energy balance that we're going to use. We'll look at some simplification with this. But this is our general form. So we have rho times the total derivative of internal energy, right, U in the fluid. Right, so remember this includes the partial derivative of internal energy with respect to time, plus that convective derivative, right? The way that internal energy of the fluid is moved into and out of a control line. plus P del dot B, so this has to do with pressure work, right, being done, so there's pressure work being done by the fluid. That is velocity, right? That is velocity, yeah, I normally have to write that for these meetings, this vector is velocity. Sorry. Del dot K grad T, so this is the heat reduction into or out of fluid element, plus this uppercase P, which is the viscous dissipation. Viscous dissipation term for the viscous dissipation or viscous work term, right? So this is basically telling us the amount of work, the amount of energy that we're losing to friction. Right, so rate of change of internal energy, total change of internal energy, pressure work, heat conduction, viscous. It does because of class. This, so that definitely does, it includes logic. Can someone help me expand that out? So total derivative, if I write dt, right? The total derivative term. What does this look like?
It's regular dt plus the gradients dotted by the whatever you're using and multiplied again by.
And let's write it out. I want to write out all the terms here. All right. So there's the u d x plus v d y plus w d. Right. So this is the partial derivative at given location of the fluid in polarity or like lab fixed coordinates. Right. This is this term here we call convective derivative. Right. So this has to do with the rate at which the quantity that we're looking at is being infected into or out of our infinitesimal fluid element. And this I've written here as a general operator, right? But if we now say d internal energy dt or total derivative of internal energy for the time, and this. Plus E du hat dy plus W du hat d. Okay.
So that u being w, that are always going to be velocity terms.
These U, V, and W, correct? These are the velocities. X component of velocity, Y component of velocity, it's E component.
And it'll be that for whatever we're doing with that.
Whenever we have a vector derivative, that's right. So we have, so in the, I'm just going to adjust the camera so it's pointing towards me. So if we look at the convective derivative, so if we look at the convective, so in the momentum balance, right, we end up with the we have the convective derivative of vector velocity, right, and vector momentum balance. That's really three expressions: one for x, one for y, and one for z momentum, right? Meaning let's say in the y, okay, so our vector velocity v, we can write it out as x component times I plus the y component times j hat plus the z component times k hat. You can also write this out in what you use the kind of bracket notation form, u v w. Or you might see this as dx u, dy, d, dt, w. Now let's say we're looking at the x component of the, the y component of the momentum balance. So that's going to be right dealing with this component of the velocity, the j component of the velocity, the y component of the velocity. Now we're going to take the total derivative of that lowercase d y component of the velocity. So then we're going to have t d dt d b, right, d lowercase d dt plus u d dx of that lowercase b plus b d dy that lowercase d y component of velocity plus w d d dc. Okay. So just as in the x component, these kind of cross terms tend to be the confusing ones, right? So this term here tells us the amount of, or it's related to the amount of y momentum being affected by y velocity, right? So it's the one that makes sense. What's this one? What is this term? Y momentum being affected by x velocity. Okay. And this is y momentum by x velocity.
Only because of this that we're looking at like these variables. You don't do it, or it's always.
Yeah, so this is what we would say is the rate of change if we are riding one particle through the fluid. This is the rate of change of velocity that we would experience as we ride through the fluid. Right, so it's still the Lagrangian derivative, but we generally deal in Eulerian terms, right? So when we're analyzing a problem, we set up a fixed control volume. We look at flow while we're fixed, sitting at some location in space, and so we deal with fluids in these terms. Yeah. I know you'll notice I often use this as shorthand for total group, right, on slides, instead of writing all out. But this expands into this. Okay, to this fold. Sorry, to this fold. So this the partial B partial T. Yeah, be careful about what we say. We say D. Right. So partial B partial T is the Eulerian rate of change of the y component of velocity. Right. Meaning, if I'm sitting at if my control volume is like this, or my experiment is like in front of the whiteboard or something, partial V partial T would be like the rate of change that I measure in velocity over time at the one. So this is because I bring this lowercase d here. So it's y component of velocity, y component of the vector v velocity. Okay. Be careful when you're writing out your notes and when you're writing on exams, right? To use notation for vectors. Okay. Otherwise, you can get a little bit more confusing, right? If you're not keeping track of what's a vector and what's not a vector, you can get more confusing. So keep track of vectors. Other questions? Yes.
What is U hat representing this?
Yeah, so U hat here is the internal energy of the fluid. Okay. Yeah, and we're using U hat here because we conserve lowercase u for the x component of the velocity. Okay. Okay, so this is what we have for our general form of the momentum balance. There was a E dot del P term in the previous form if you were paying attention to that previous form. The combination with momentum balance actually got rid of that term. Sorry, this one, yeah. So this, can someone else explain what is this term here? Viscous precipitation, right? So this is the amount of energy moving the fluid that is lost in viscous friction, right? The fluid layers sliding or moving relative to one another, causing friction. Just like in two solids, but in a fluid, it's driven by viscosity. Okay, we're actually going to talk about this term. Actually, this is the definition of that term. So, for a Newtonian incompressible fluid, this is the definition of that full term, capital T. I encourage you to, pull up your notes, pull up the slide. What we can see, so important things to know here, just the key things to know here. It depends on mu, right? It depends on the fluid viscosity mu, right? And it depends on the derivatives, right? The partial derivatives of the velocities, right? So if we have, for example, the x velocity varying the y direction, right? Meaning the velocity in the x direction is a function of y. Like let's say we have flow between two flat plates. Example that we'll look at probably on Friday. We'll see that we've looked at in the past. We know that the velocity of the fluid in the x direction is a function of the y component, meaning that we have, this implies that we have pieces of fluid as we move in y, we have pieces of fluid that are traveling at different velocities relative to their neighbors. And that gives rise to friction, right, through viscosity. And that friction through viscosity can pull energy out of the fluid, and that is small encapsulated fluid.
Real quick, Ron, what does that second term E times?
Anyone say, what's the second term represent? Pressure work. Yeah, it's the second term is pressure work. How do we use for it? I mean, they should. And in this term, should have the same dimensions of these that energy per time. Yeah, that should be the dimensions of this. Yes. Not the second derivative, just the first derivative. Yep. Okay, so we're gonna look at an example, actually not for energy balance, but for maximum momentum balance again of the flat plate moving. We have considered previously, but we're going to use nanoscopes to get there. And we'll see that, for example, in nanoscopes, there are a lot of terms, maybe not as many as we see here, but there are a ton of terms in nanoscope equations, right? But generally, for the kinds of flows where we can solve them with pen and paper, most of them will drop. So we'll say like, for example, in the flat plate example, we had we're looking at this dissipation term in the flat plate example. The u is just a function of y, v is 0, and w is 0. So u dx is 0, v is 0, so dv dy is 0, w is 0, so wdc is 0. E is 0, this term drops out, this term doesn't drop out, this term remains. This term drops, u is only a function of y, this term drops, and just have one. Right. So and we'll see this again in the momentum balance way. So something that we can address on that paper. We're going to use most of these terms at the very start. So it looks scary. But it's good. So, yes,
So just to be clear, this equation, the difference that was only in relation to this way, in this space.
no, this is the full energy balance for differential control volume, right? Because we have the rate of change of internal energy within a fluid particle is pressure work, right? We can change energy by doing work on it with pressure. Change energy by adding heat or taking heat away. Change that energy with this work. So it's a full energy balance for fluid.
So in that case, when this is worth just changing fluid energy. Since you're
Yeah, so this is the same with energy balance, keep track of everything here. So one of the main functions, for example, we assume it's isothermal, right, then this thing would drop out. And we would see that, and if we assume isothermal, then oftentimes the internal energy is not going to be either. Right? You realize here. So then we would see that, this bit is kind of that, within the fluid we have, kinetic energy converted into, pressure. This is our final result. Energy change in fluid particle pressure work plus some mixing. We have 4 terms. This is a pretty general form of the heat balance differential equation. It's valid for a Newtonian fluid. So it has to be so that we've already written that P, it's only valid for Newtonian fluid, it's valid if it's unsteady, it's valid if it's compressible, it's valid if it's conductive heat, right? We have a temperature profile. It neglects radiation heat transfer, which can sometimes be important in high temperature fluids. We neglect any internal sources of heat, so if we have some chemical reaction occurring, then that would add another term, right? For example, this is right. But this is fairly general form of the balance equation. So now we're looking at simplifications to this, right? For the same kind of level that we call for all the other balance laws. We'll look at simplification of this expression. So we assume that, for example, internal energy is related to heat capacity and temperature. We assume constant fluid properties, and we assume that the fluid is incompressible. Then we obtain this form of the expression. Which is far easier to solve, right? So now we have written out most everything in terms of just the temperature, right? So we reduce this expression to primarily just about temperature. And we're saying that the rate of change of temperature now, we're relating rate of change of temperature within a fluid particle, moving through the fluid, or total derivative of temperature, heat conduction, plus that physical dissipation, right? Turning kinetic energy into in this case, we can solve for velocity first. So typically, we have an expression like this, we solve for velocity first, and then worry about temperature later. So this makes it the solution process a lot easier. So first we deal with Navier-Stokes, for example, and then we deal with this expression. So in summary, we have 5 basic equations, right? So we have continuity, which is our mass conservation equation. We have momentum, but remember, this is really 3 equations in one, right? It's a vector equation. Momentum is a vector quantity. And we have energy, right? So this is the form of the energy balance that we did. So this is five equations. In general, for a fluid, we have 7 unknowns in here. Right? So we no longer have that nice Navier-Stokes. Instead, we have 4 equations, 4 unknowns. But it's still challenging to solve. Here we have 5 equations, 7 of those, so we need something else, right? Density and internal energy were generally going to be determined by some kind of thermodynamic state relationship. So we assume perfect gas, constant specific heat, right? So we assume constant specific heat, for example, in the previous slide. And with that, we can then close these. But in order to do anything with this, we still need initial and boundary conditions, right? So we now we have differential equations of fluid motion and energy balances in a fluid. But in order to solve these equations for any kind of a real case, we need both initial and boundary. Right. So even if we wanted to, so for example, on Friday, we're going to revisit flow between 2 flat plates. But we need to find our boundary conditions in that case. So I want to talk a little bit about what kind of initial and boundary conditions we can, especially what kind of boundary. As far as initial conditions for a problem that's unsteady, meaning it's varying in time, we need to know all of the properties of the fluid, for example, at time t being 0. So I just want to go back. So let's confine ourselves to let's say just the Navier-Stokes. So we consider it's all the way back. So we have the Navier-Stokes equations. Right, so we have delta V is equal to 0. We have our momentum balance Navier-Stokes. 4 equations, 4 unknowns. We've known these equations for 200 years, right? Almost going on 200 years now. And they haven't really changed. They haven't really changed. In some sense, solving a problem in fluid mechanics is all about defining initial and boundary. Defining our assumptions and defining the. So for example, when you're solving a problem in CFT, you are typically using the Navier-Stokes solver. We're just using Navier-Stokes solver. And what differentiates one problem from another is how you're defining those initial and boundary. So, in some sense, the most important part of the problem, or at least the thing that differentiates one problem from another, are those initial and boundary. So sometimes there's a lot of focus on the equations, right? What equations. When we know fluid mechanics, we generally know the equations. But the initial and boundary conditions have been applying and closing those, that's where things get more challenging. That's where we go from flow between 2 flat plates, where based on the we'll consider steady state, so we don't worry about initial conditions. And boundary conditions will be no slip but either flat plates. And we'll get a solution that we can write on the board, right? We can derive regulated class. We'll get some these equations right on the board and write out regulated class. But if we have flow over like an airplane, Boeing 737 or something, it's the same equations, but we have different surfaces, right? So therefore different boundaries, different boundary conditions. That make solving these equations far. So boundary and initial conditions are, in some sense, the whole problem. Not we're using the same equations. Yeah. In terms of surfaces, the next week we're only dealing with flat stuff. Yes. We're only dealing with flat. I mean, for a very simple curve surface. Something that is I think we're rolling with rolling. Excuse flat. So in general, for a complex curved surface, at this point in like humanity's interact with fluid mechanics to deal with which means you have a lot more to learn to really good. So, just because, I just want to stress that TFB is a topic in us, and we do not have all of that. So, to me to know, all of these properties at T equals 0, we also need to know the values of these things at the boundary. And so we're gonna talk about this, on Friday, but one example we've already seen is the no slip condition, right? So we're generally gonna assume the velocity of the fluid is equal to the velocity of the wall whenever a fluid encounters, the wall, in this case it's solid. So again, illustrated here, where this is a perfect flow in a round, tube. We can see that perhaps counterintuitively, the velocity really is 0 at the wall. So no slip condition. So on Friday, we'll have our YouTube videos. We'll talk about boundary conditions and the different types of boundary conditions we can encounter. And we'll do that flat plate example again. Sorry. See you all Friday.